Welcome to this class on hardware security. So, we shall be discussing on what we were essentially we shall be continuing on what we were discussing in the last class on various hardware techniques for implementing advanced encryption standards. So, to start with, today we shall be discussing in details about how we can express the entire AES in composite field, something that we were already discussing in the last class. We shall continue with that. In particular, we shall be looking into how a mixed column is implemented along with an SBox or various approaches for implementing SBoxes. So, and finally, right, we shall be looking into how we can design and we shall be also looking into how we can design a combined structure between the encryption unit and the decryption unit, that is how we can combine the encryptor and the decryptor of AES. And finally, take a look at one of the very new or like relatively new implementations on AES, state of the art implementation of AES, which is integrated in most of our modern Intel processors. So, with this background, right, let us take a look into what we have to discuss. So, to start with, we have already discussed this in the last class that suppose let us consider the AES subbyte operation. So, this is the essential steps that we do in the AES subbyte. We take a finite field inverse, we do an affine transformation, that means we pre-multiply with a fixed matrix A followed by adding the vector B. So, now one approach could be that we do this in composite fields, but when we do this in composite field, there is always a conversion that we do from the standard field to the composite field and back. So, this will incur an overhead. So, one approach that is essentially advised is that let us transform the entire AES in composite fields. So, that at the very beginning, that whenever I have the raw plain text and the key, there we do a transformation into the composite field. We do the entire AES in the composite field, not only the subbytes, but also the other operations like mixed columns and things like that. And finally, right, we get the result, that is the ciphertext in the composite field. We bring back the result to its normal field by taking the inverse mapping or applying the inverse mapping. So, in this case, let us take a look about that like suppose it is not only that the inverse has been done in composite field. What if I do the entire subbyte operation in composite field, that means along with the affine mapping. In that case, what we have to do is that we have to slightly adjust the matrices A and B if you want to do the operation in composite field. So, how do we do that is illustrated here. So, if I apply the transformation from GF to the power of 8 to the composite field, say GF to the power of 4 squared by the mapping T or the matrix T, then essentially we know that y dash is equal to T y. So, we apply T on both sides of this equation. So, we get T A x inverse plus T b, that is T has been applied to both A x inverse as well as B. Now, we can easily write T A x inverse as T A T inverse multiplied with T x inverse. So, note that T inverse with T is I or the identity matrix and plus T b. So, this T A T inverse is what I call as A dash, and this T x inverse or T applied on x inverse is what is called as x dash, okay, and T b has been denoted as B dash. So, therefore, these are my transformed affine matrices A and B. Okay. So, they have been updated by T A T inverse and B dash has been updated as T b. Okay. So, an important point which may be emphasized here is that because of isomorphism property, note that what we are doing right here is important to observe. So, what we are doing here is we are basically denoting this T x inverse as x dash, right. So, as if this is the inverse in the composite fields. So, note that it is correct. Why? Because of the isomorphism property, one can calculate x inverse in the original field and then transform by applying T, it can transform it into the composite field, or one can also apply or convert x directly into the composite field and then take its inverse, right. So, therefore, this is an identity because of the isomorphism property. So, that implies that I can substitute this T x inverse as T x whole inverse. So, that means what? That means I am doing the inverse in the composite field. X was originally in the GF to the power was in GF to the power 8. By applying T x, I have transformed it into the composite field, and now this operation, right, is done in the composite field. Okay. So, that is why this equation, that is y dash equal to A dash x dash plus B dash, is in the composite field. That means, x dash is in the composite field, A dash and B dash also has been adjusted to do the transformation in the composite field without requiring this transformation from the GF to the power of 8 to GF to the power of 4 square and vice versa at every step. Okay. So, that is why you now have a consolidated sub bytes, which where this entire sub bytes has been expressed in composite fields. Okay. So, that will reduce your overheads incurred due to field transformations. So, now there are some more interesting observations here also, like here is an example. So, the irreducible polynomial that we choose here, so that is as we have discussed in the prior classes as well. We have got say y square plus y plus tau, where tau is a primitive element of GF to the power of 4. Okay. So, we choose, so this is an example of tau that we choose, say tau is omega power of 14, where omega is x, that is 0 0 1 0. So, this is like just an element in GF to the power of 4, and we raise it to the power of 14 to serve as a value of tau. Okay. So, you can have different such values of or such possible candidates that you can choose, but it is important to note that the tau is a primitive element of GF to the power of 4. Okay. So, as we know that there are different primitive elements of GF to the power of 4. So, you can actually play around with those values, and you can like if you choose different values of tau, you can easily understand that you will get different choices for the matrix A or A dash also. Okay. So, in this case, for example, a key point is that depending on the choice above, the matrix A dash will change, and therefore, it will have different 0 1 values. Like for example, in this case, the value of or the matrix A has been transformed into A dash, and it looks like this. Okay. So, you can observe that the number of ones in the original matrix of A is significantly large compared to the number of ones which you have in A dash. Okay. And therefore, right, it is an interesting choice, because in this case the number of ones is around 40 and here it is around 18. So, therefore, the number of gates or the number of XORs which you will require to implement this transformation would be much less when you are doing the operation in the composite fields. Okay. When you are doing it in composite fields. So, therefore, this naturally gives a nice mechanism of how you can reduce the cost of your implementations. Okay. So, you can try to play around with different choices, and you can try to see where you get exactly minimal number of ones, for example, in A dash. Okay. So, it could be an interesting exercise in itself. So, therefore, right, I mean we would like to now transform. So, let us take a concrete example. So, we are suppose transforming GF to the power of 8 to GF to the power of 4 square, and we have already discussed about efficient techniques and techniques about how we can do these transformations previously. But note that in the efficient technique that we discussed right in the last class or in one of my last classes, there the polynomials. So, we did a mapping of the basis vectors. Okay. So, in that case, right, the field polynomials were assumed to be a primitive polynomial, but note that in case of AES, the polynomial R z, which is equal to z power of 8 plus z power of 4 plus z power of 3 plus z plus 1 is irreducible, but is not primitive. Okay. So, we do not directly apply that technique, but rather since the field is small, we can actually do our exhaustive analysis. Okay. So, what we can do is that we can take the primitive element of GF to the power of 8, say gamma, and we can map it to a primitive element of GF to the power of 4 square, say alpha. Okay. So, what we can do is for all the values from 0 to 255, that means for all the 256 values, I just do this mapping gamma power of I to alpha power of I and get a mapping. Okay. So, it is interesting to check that whether the multiplicative homomorphism and the additive homomorphism are satisfied for these choices. Okay. So, like suppose we get such a nice map, I mean it is done like we get this mapping and it satisfies the multiplicative and the homomorphic property, then this is a candidate matrix. Okay. So, you can again like you can get different matrices, but this matrix is say our choice. Okay. So, you can get more illustrations about this matrix in this paper, which was published in Chess in 2001. So, in this case, right, if you take this mapping, there are certain interesting points that you can observe is that the last column, for example, in this matrix is 1, which means like a unity element in GF to the power of 8 will get mapped into GF to the power of 4 square also as a unity element. Okay. So, likewise, right, you can also observe that a 0 will get mapped into 0, because that is obvious. But for the other parts, right, it is interesting that to see how they work. Okay. So, I give you an example here of how the mapping looks for a non-trivial input. So, for example, 2, right, is an element in GF to the power of 8, suppose the 2 is a field element. You can also write 2 in curly braces to indicate that it is not 2 per se. So, you can actually like denote this 2 as this value, say 0 0 0 and 0 0 1 0, that stands for x basically. So, therefore, T2 would be in now GF2 to the power of 4 squared. So, if I apply this matrix on 2, then I should get the result in my composite field GF2 power of 4 squared. So, this turns out to be this column here, that is this column, because note that there is only 1 1 here. Okay. So, therefore, this turns out to be this column, and that is 0 0 1 0 followed by 1 1 1 0. Okay. So, now note that this element is in the composite field. So, how do we read this? So, this part is my top part, that is this part has got is the coefficient of x, okay, whereas this part is the constant part. Okay. So, therefore, this part has the coefficient value here is alpha, because here the coefficient is itself it can be denoted as alpha, where alpha is a primitive element of GF2 to the power of 4. Okay. So, you can also say that in GF2 to the power of 4 this is again x, okay, where you are using 4 bits to denote the value. Okay. So, likewise this value 1 1 1 0. So, I leave it to your exercise to verify that you can take alpha, and if you raise it to the power of 11 and do a modulo, right, which is x power of 4 plus x plus 1, which is an irreducible polynomial in GF2 power of 4, then you will get alpha power of 11. Okay. And if you get alpha power of 11, then this alpha power of 11 stands for this vector, that is in this in the field GF2 to the power of 4, this is x cube plus x square plus x. Okay. So, you should get that value. So, if you do that, right, in a compact way, you can denote them as alpha x plus alpha power of 11. Okay. So, now the reason why I show in particular for 2 is will be understood if you consider now the mixed column matrix. Okay. So, remember that in the mixed column matrix we have got these elements, and as I said that I now want to express the entire AES in composite fields. It means that I have to also transform these elements into the composite fields. Okay. So, these are constant elements, they need to be mapped into say T2, T3, T1 and so on. Of course, T1 will be 1, but T2 and T3 will be non-trivial. So, you have to basically calculate it. Okay. So, therefore, right, T1 is T1. So, remember that when I am doing this operation, then my elements that I am multiplying them are now not in GF2 power of 8, but in GF2 power of 4 squared. So, therefore, they will be represented as say A1x plus A naught. So, if I multiply with T1, I will get A1x plus A naught, because T1 is 1 itself. For T2, right, T2 when I multiply with A1x plus A naught. So, note that T2, right, essentially is, as we have found out in the previous discussion, it is alpha x plus alpha to the power of 11. So, therefore, I will take now alpha x to the power of 11 and alpha x plus alpha to the power of 11 and multiply it with A1x plus A naught. Okay. So, again I leave it to as an exercise to check that this equation will be satisfied. You can observe that when there will be instances when you get x squared, but that x squared needs to be converted back into the field GF2 power of 4 square by taking an XOR, or by considering modulo with this polynomial, which is an irreducible polynomial of the composite field GF2 power of 4 square. So, what is the polynomial? X squared plus x plus alpha power of 14. So, therefore, whenever you get x squared, you substitute that with x plus alpha power of 14. So, if you do that, right, every element here can be represented in this form of A1x plus A naught, where A1 and A naught are elements in GF2 power of 4 square. So, in this case, right, you will get this particular example here. So, therefore, you can observe that you are essentially doing more operations, in the sense like you are doing additions, but note that the multiplications that you are doing are now in the smaller field, which is GF2 power of 4, and that is much more efficient than when you are doing one operation in GF2 power of 8. Okay. So, therefore, right, there are some constant multiplications. So, for example, alpha power of 11 is a constant and so on. So, therefore, these multiplications for these multiplications you do not need a dedicated multiplier, but you can actually do it in a much more efficient manner. Okay. So, finally, right, you can also note that T3, when you are doing T3 into so that is how you are doing T2, but when you are calculating T3, right, and multiplying it, you need not again multiply with T3, but rather you do a T2 into this plus the original value. Okay, like with what we did for the original mixed column operation, instead of multiplying 3 into x, we did 2 into x and then added x. Okay, so, you can again apply the same approach even in the composite fields. Okay. So, once you have done that, essentially you have transformed the entire operations, like you have transformed the mixed columns, you have transformed the shift rows, essentially will be simple because it is just wiring. So, there is nothing to be altered here. The byte sub or the sub bytes we have already seen how to transform. The add round key again will be again similar. So, you need not make any drastic any difference there. So, therefore, this is how your encryption flow will probably look like. Okay. So, now I want to create its decryption algorithm. So, suppose I want to implement in one single chip, I want to implement both the encryptor and the decryptor. Remember that this is a very like a viable requirement when you want to like put your encryptor or encryption in a transmitter, which can work both at the transmission unit as well as receiver unit. So, you need both the encryption unit and the decryption unit in situ inside a single chip. Okay. So, therefore, one thing you can observe here, that when you are seeing the decryption operation, then this is just the decryption is just the reverse of encryption, right. So, therefore, here the final steps are if you observe, you have an add round key and then you are giving the ciphertext, you are exporting the ciphertext. This should be the first step when you are doing decryption. Okay. So, likewise note that in the first round there is no mixed columns, or in the final round there is no mixed columns. So, you have got a byte sub shift row followed by add round key. When you are doing the inverse, you are doing an inverse shift row which just cancels out this shift row operation. You are doing an inverse byte sub which cancels out this byte sub operation, and then you are again doing an add round key, or which is again the add round key, the inverse of the add round key is add round key itself, because add round key is an idempotent operation. So, it is self invertible. Okay. So, you need not do any change over there, and then you essentially do the remaining steps. Okay. But we can easily observe that here, if you have got a single chip to work as both, then the operations are not exactly synchronized. Like when you are doing a byte sub here, you are doing say an inverse shift row here. So, basically it implies that it looks like you need two separate dedicated paths for doing this to do this design in a single chip. Okay. And that may have a cost, because that may have like an overhead that essentially can come up. But it turns out that for AES you can actually you employ a couple of very simple tricks, and you can rewrite this in this way. So, you can write this such that exactly they are balanced. Like if you are doing a byte sub here, you are doing an inverse byte sub here. If you are doing a shift row here, you are doing an inverse shift row here. If you are doing a mixed columns here, you are doing an inverse mixed columns here. Okay. There is a small change that you have to do. The change is that for the round keys, like which are intermediate, that is if you leave out the first round and the the last round key, then you have to apply an inverse mixed column operation to those. So, you have to slightly adjust the key scheduling, okay, and that should be fine. I mean, you should be essentially able to get a decryption flow which nicely synchronizes with the encryption flow. So, how does it work? So, there are some two simple points to observe here. The first thing is that the order of the inverse shift row and the inverse shift bytes are indifferent. Okay. So, you can actually easily swap them. Okay. The second thing is that the order of the add round key and the inverse mixed columns can be inverted if the round key is slightly adapted. Okay. So, let me quickly talk about this point here, which may be little non-trivial to see. So, I will try to explain this by this illustration. So, suppose you have got a simple linear transformation which you can think of your mixed column operation, okay, or mixed column means like it's a linear transformation. Okay. So, therefore, I denote that by a matrix L. So, the previous operation, right, say the add round key which you have done prior to that is denoted here as XOR. So, when you are doing X XOR with K and then you are applying this L mapping to get X XOR K. So, now suppose I want to swap these positions. Okay. That means, I want to kind of push this XOR through the linear layer. If I do that, then essentially it turns out that I am basically bringing the L before and I am pushing the XOR later on, but it is easy to see that if I just make a small modification to my to the key, that means I pass the K also through a linear layer, then the output remains the same, right. It is again L of X XOR K. So, therefore, you can actually do this swap, but you have to just make a small change to this L layer. Okay. So, therefore, depending upon whether you want to push the L before or you want to push the L later, right, you essentially have to make a small adjustment to the secret key or to the round key. Okay. So, that is exactly being done here, and I try to explain this by a 2-round AES variant. Suppose you take the add round key where this is your input, you have got the state, this is your expanded key 0, then you do a sub byte, then you do a shift row, then you do a mixed columns, and then again you do an add round key. Note again that in the last round you have only a sub byte and a shift row, and then you do an add round key. Okay. So, this is a 2 round simple variant of the original AES. Okay. You can easily, without loss of generality, extend this to 10 rounds of AES 128. Now, if you consider the decryption unit of this, I have to again, as I said, work behind like this. Okay. So, I have to start with this, do the inverse operation of this and so on. So, then it turns out exactly like this. So, I do the add round key now with the state expanded key 2, that is the final round key. I do an XOR, I do an inverse shift byte, I do an inverse sub byte, I do an inverse shift row, then I do an inverse sub bytes, then I do an add round key, inverse mixed columns, inverse shift row, inverse sub bytes, and finally an add round key. Now, note that by the observations that we discussed just now or just prior to this, you can actually change few of these sequences. Okay. For example, I can easily interchange the shift row and the sub byte operations. I can bring the sub bytes before, I can push the shift row operation down. Okay. And likewise, I can also swap this inverse mixed column and the add round key, but I have to make a small change in the expanded key. Okay. So, when I am pushing the inverse mixed columns right before, then I have to apply, in order to cancel that effect, I have to apply this operation also on the expanded key. Okay. In order to counter that. So, what I do is this. So, therefore, when the moment I change this, right, see, I have brought up the inverse sub byte, pushed back the inverse shift row, I have changed these operations, it is fine, but only I have to replace this expanded key by an equivalent expanded key, which is nothing but applying the inverse mixed column on the key. Okay. So, if you do this, right, then essentially now and now observe on this the way of writing the decryption, you can see that it is exactly the same, or it looks exactly like the same as your decryption flow, as your encryption flow. Okay. So, therefore, they are nicely balanced, and therefore, you can essentially kind of share the hardwares and you can do them in parallel. Okay. So, once you have understood this, right, now we are in a position where we can share between the sub byte and the inverse sub byte, we can share between the mixed column and the inverse mixed column, and try to see whether we can save some gates. Okay. So, therefore, right, there are a couple of interesting techniques which people have proposed. For example, right, so this is what we have already discussed, that the equivalent key schedule can be obtained by apply the inverse mixed columns after the key scheduling algorithm, and this can be generalized easily to the full round of AES. So, thus we see like that the equivalent decryption, the sequence of the steps is similar, and this helps in implementing an encryptor and the decryptor on a single chip. Okay. You can essentially share between the encryption and the decryption flow, and you can get a nicely optimized design. So, therefore, right, you can actually go for a compact encryption and decryption architecture. So, where you can merge the operations in the encryption and the decryption into a single unit. For example, right, you can observe here that what I have tried to do is that I have tried to kind of represent this, if you compare with this with the architecture that I had in the last class, where I had a separate encryption and the decryption block. But now we are trying to think that whether we can combine these two blocks into a single block. Okay. And that can save some gates, which is very important for our hardware designs. Okay. The rest of the things remain same. Okay. So, now therefore, let us try to see how we can merge. Add round key is of course the same in both encryption and decryption. The shift row and the inverse shift row only differ in the direction of shifting. So, they are pretty easy to kind of do it in a single hardware. You can just slightly program the hardware and it should work in both the operations, both in the encrypted unit as well as in the decryption unit. But what is interesting is to see how we can merge the mixed columns. Okay. So, there are a couple of interesting approaches which people had proposed. For example, right, I mean this is an example where you are essentially trying to merge the mixed columns. Okay. So, note that in inverse mixed columns, right, the matrix is slightly different from the mixed column matrix. It's not slightly, it is actually significantly different from the mixed column matrix. While in the mixed column matrix, you had nice operations like 2, 3, 1 and so on, which were easy to implement, but in the inverse mixed column, we have got pretty non-trivial values, which essentially are are not easy to implement. Okay. For example, you have got the values like E, B, D and 9 and so on, which are not easy to implement. So, how do you essentially how you can efficiently implement them, in particular when you already have a mixed column implemented. Okay. So, one of the approaches which was proposed by Sato in AsiaCrypt in 2001 is as follows. You write this matrix of inverse mixed column and express it as summation of the original mixed column matrix with 2 more factors. So, one of the factors is as shown here, and the second matrix is shown here. Okay. So, you can easily observe that these matrices are pretty easy. I mean, in the sense like they are all powers of 2. Okay. So, therefore, they should be easy to implement. So, therefore, right, what you can do is that you can essentially have in one flow the normal matrix. Okay. You can have and in this other place you have this element, this particular matrix, and therefore, right here you can get the original mixed columns, but when you bring in this particular thing and you XOR this with this, then you get the final inverse mixed columns. Okay. So, you basically can essentially share the like utilize the origin or the already hardware which is present in the mixed columns, rather than having two standalone one mixed columns and one inverse mixed columns. So, when you are doing inverse mixed columns, you are also using the hardware which is already there in your mixed column matrix, okay, or for your mixed column matrix. So, it turns out that when you are doing a separate implementation, then it requires something like 592 gates, whereas if you do this merging, then you need something like 195 gates. Okay. So, that is a significant improvement. There is a slight increase in the delay, because now you have to wait, the critical path will slightly increase, but the critical path increase is not as much as the saving that you get. For example, it goes from something like 5 gate units to 7 gate units. Okay. There is another interesting approach which was proposed later on, which is essentially where you basically like factor this mixed column matrix. So, if you factor this mixed column matrix, then also you have got one of the factors as the mixed column matrix, whereas the other one is as shown here. Okay. And this is again like not very costly to implement. So, it turns out that this requires something like 166 XORs, and of course, there is a 32-bit mux. Okay. So, here also you have around 195 units, and here you require around 166 XORs. Okay. So, therefore, you basically have got a mux which is over there, and then you follow it by an AES mixed column operation. So, in one case you are basically passing it through this matrix followed by a mixed column to give you this inverse mixed column operation. On the other case, when you are just using it for the encryption part, that means when you want it to get configured as only the mixed column, then you have to bypass this operation. So, you basically go through this path and you just apply the mixed columns. Okay. So, again you have got a shared mixed column and inverse mixed columns operation. So, likewise, right, you can also merge the SBoxes. So, when you merge the SBoxes, then again there are certain certain improvements that you can do. But so likewise, right, as we have seen that how we can merge the mixed column operation and the inverse mixed column operation. So, likewise we can also merge the SBox and the inverse SBox operations. Okay. And that can also lead to opportunities of saving. So, here is an example how we can do that. So, if you remember, like when you are doing the x or the SBox x. So, when you are doing the forward transformation, so you take x, you map this x say to GF to power of 4 square, which is in the composite field. Suppose you do the inverse in the composite field, okay, and then you do the reverse map. Okay. So, then you bring and so if you do that, right, then you get x, I mean you get SBox x. So, likewise, right, when you are doing decryption, you take SBox x, you do the inverse operation, that means the inverse mapping, you apply the reverse affine operations, you can combine these two things to save some gates, because both of them are matrices, and then you pass them through an inverse which is in the composite field GF to power of 4 square, and finally you do the reverse mapping to get the result back, which is in this case x. So, you have basically fed in SBox x, and since you are doing the inverse operation, you are getting x back. Okay. So, it is fine, because the core operation in both the SBoxes as well as the inverse SBox is the finite field inverse. Okay. And that is the major hardware which you are trying to share in both the data paths. Okay. So, for example, right, if you go now if you compare it with say one standalone SBox and an inverse SBox, then you would probably require something like 362 NAND gate equivalents in a standard cell estimation. If you combine them and merge them, then it reduces to something like 234. So, that is a significant amount of reduction in the gate count. Okay. So, therefore, right, I mean of course, you need to implement the inverse in an efficient manner, and that is essentially studied in several works. In particular, it is nicely described in this paper by Canwright, which is a very compact SBox for AES, and it is a very pioneering work on how you can efficiently implement the SBox in composite fields. Okay. So, therefore, right, I mean there are different schools of design, and here is a quick snapshot on the objectives. So, therefore, some people have worked for latency, some people have worked for area. So, therefore, like you would probably try to place your design into different points in this spectra depending upon your application. Okay. So, here are some bunch of interesting references which people have like developed to design efficient AES implementations. Okay. So, therefore, for example, right, I may my focus may be only to make it very high speed, in which case I should be looking for designs which are in this part of the spectrum, whereas if I want a lightweight design, then I should be looking maybe at this point of the spectrum, whereas if I want both, then probably I should be looking at these points of the spectrum which are which kind of nicely trades off both area as well as latency. Okay. So, in particular, right, this implementation which is shown here by Alam in date 2007, right, then here in this design we try to develop an AES which supports both for all the 3 configurations of AES like 128, 192 and 256, and still essentially trades off nicely the area as well as latency. Okay. So, it can be an interesting read for our purpose. So, let me just conclude with the state of the art discussion. So, Intel has introduced dedicated hardware for AES on its microprocessors. These are accessed by dedicated AES instructions, often called as AES NI. So, this AES design consists of standard cell designs, approaches standard cell techniques. So, it is a very interesting and very nice piece of engineering work. The techniques that are followed again are essentially what we have already been studying in this class, like composite fields, single map, reverse map. So, these are exactly that what we have studied, but the engineering is so nice that it ends up in realizing a speed of 53 Gbps obtained by a fully custom design flow on 45 nanometer technology. So, this was published in VTS 2010. So, some of you who are interested can go through this paper. Here is a sort of a pictographic diagram about how the architecture looks like. So, if you see now carefully, the ideas are essentially what we have already been studied. For example, the plain text is mapped to GF2 power of 4 square, and then the operations are done in the composite fields. Okay. So, there are all these SBoxes which are placed over there, and this is and finally, right, there are depending upon the configurations, there are different iterations which are set, like there are either 5 iterations or 6 iterations or 7 iterations, and finally you get back the result which is in the composite field. So, you do an final mapping or the reverse mapping from GF2 power of 4 square to GF2 power of 8. So, therefore, this mapping, right, like which is shown here by the shaded boxes, are done only once. So, you are not doing any intermediate transformations, you are representing the entire AES in composite field, and as we have discussed, like the mixed columns, the affine transformations for subbytes, all of them are transformed into composite fields. Okay. So, the entire operation is done in composite field. Okay. And that essentially gives an opportunity of a very high throughput AES implementation, okay, which can be realized in our Intel processors. And as we shall discuss later on, right, this essentially also gives us a lot of nice properties, in the sense like it not only reduces latency, but it also helps you to protect against several side channels, in particular software side channels like cache timing attacks, okay, which we will be discussing in our future classes. So, let me stop here. So, again this is my standard reference that I have followed for the book, followed for the class. And to conclude, like we have been discussing about how we can express the entire AES in composite fields. We have discussed about techniques using isomorphisms which are efficient for SBoxes. We have discussed about how we can combine efficiently the mixed column and the inverse mixed column operations. We have discussed about how encryption and decryption of AES can be made similar by using its structures. And finally, we have discussed about how the general observation is that when you are combining encryption and decryption, then it saves valuable gates. Okay. So, with this I would like to stop here, and thank you for your attention.